can start.
Okay, yeah. So, hi everyone, I'm Mizna. I'm a PhD student from India, and I'll be presenting a few observational evidences of an FU Ori-like outburst from an object which was previously classified as a very low luminosity object. So, to begin with, well-lows or very low luminosity objects are embedded protostars with luminosities less than 0.1 times solar luminosities. And these are considered as an extreme case in the luminosity problem. And because of their very low accretion luminosities, they're considered to be either very early stage or extremely low mass protostars or even proto ground dwarfs because their evolutionary outcomes are still uncertain. So as we all know, the solution to this very low accretion rates can be episodic accretion, and these vellows represent the more of the episodic accretion process. And there have been multiple studies that probe the evidences of fast accretion bursts in these vellows with indirect methods such as the location of CO and N2H plus snow lines, CO outflow signatures, etc. And particularly the Shea et al. 2018 and their team found that out of almost 90% of the sources in their sample were showing signatures of fast accretion bursts. But direct observations of outbursts in these very low luminosity objects are really rare. And in this presentation, I'm going to tell about one such outburst that we discovered. And the source which is under outburst is SSTgbs J214706. And it was found to have a rising mid-IR light curve for almost 12 years in the Park et al. 2021 study. And as you can see on the left side image, there is a clear brightening event from 2010 to 2022 in the mid-IR. And this outburst object was identified as a class 1 YSO within IC 546 and at a cluster distance of 786 parsecs. And the pre-outburst luminosity was calculated to be approximately 0.06 based on its Spitzer photometry. And Park et al. 2021 identified that it shows an increasing mid-IR light curve for the past 12 years with approximately 1.78 magnitudes and 1.84 magnitudes in W2. And one interesting fact about its brightening was that the e-folding rise time was approximately 7 years, which is almost 50 times larger than the prototype FU Ori. And we decided to spectroscopically follow it up. And then another interesting thing happened that we identified that it was part of a binary, a potential binary. So 2021 and 2022 images on the middle and the right, that these are the acquisition images in K-band from Gemini and IRTF. And we see there are two sources along with an extended emission. But when we compare it with the 2011 Euclid's K-band image, we see there is only one source and the extended emission is also missing. This was an indication that the source SC, which was absent before and which appeared in the recent images along with the nebular emission, is the source under outburst. And wanted to check whether the NEOWISE images from multiple epochs show any trend towards this. So what we tried was we calculated the center of brightness or the centroid of the source from all the epochs of NEOWISE images. And we see that there is a systematic shift towards the source SC during the epochs, like during the brightening event. So this shift is seen in like divided into two because of the odd and even NEOWISE was showing a slight shift in array. So both of these groups, like the even and odd epochs, was showing a similar trend of approximately 0.4 arc seconds towards SE. So this was another indication that SE is the source under outburst. So in order to calculate the pre-outburst luminosity of the source, we gathered all the photometry available, and from including the Spitzer 3.6, WISE, and Herschel, as well as the Scuba 450 and 850 fluxes. So by fitting the Robitali 2017 WISE models, which has a star, a disk, and an envelope system, we calculate its integrated flux over the fit comes out to be approximately 0.25 times the solar luminosity. And I would like to point out that this is the bolometric luminosity, which is an upper limit, because at most of the longer wavelength end was the source was not resolved, and we assumed that the emission was solely from this outbursting source. So this bolometric luminosity is the upper limit. So from this bolometric luminosity, we calculated the outburst luminosity using the relation from Contreras Penn et al. 2020, using the relation, the increase in the mid-area flux is proportional to the luminosity raised to 3 by 2. And using this relationship with our previously calculated pre-outburst luminosity of 0.25, we get an outburst luminosity equal to 0.95 times solar luminosities, which is quite less compared to the luminosities of other FU Ori-type objects identified. And coming to the spectral characteristics, we have the separate spectrum for both of these components, which we named the northwest and southeast components. And we see that there is a CO absorption feature on both. And particularly in SE, which is the source under outburst, the CO are much deeper than the NW component. There are weaker NA and CA emissions, and bracket gamma is completely absent. So is for the other emission lines. Most of the emission lines are absent. And we wanted to try how we just try to spectral type these objects using the IRTF spectral templates. And we found that when we use the spectral templates, the SC component, the outburst, was not properly fitting over any of the spectral templates, except that towards the red part, it fits on an M-type star. And when I added an FU Ori type of spectrum, that of V2775 Ori, we found that it was on top of our observed spectrum of SE. And for the other component, it was fitting with a G-type star. We further investigated how closely our spectrum resembles V2775. As you can see on the bottom panel, the red curve indicates our source, and the green dashed curve is the V2775 Ori. So as you can see, the spectrum closely resembles V2775 Ori, and even all the absorption features are shown in the spectrum, whereas the N component is not as deep as the V2775 Ori spectrum, and some of the absorption features are missing as well. So in order to further confirm, we calculated the equivalent widths of CO and NA and CA, and we reproduced the plot from Conley and Rayford 2018, which segregates FU Ori-type objects from class 1 protostars. And as we see here, the equivalent widths that we calculated from the spectrum of SC falls the location of typical FUOs or peculiar objects, whereas the NW component falls on the location of class 1 type stars. So this was another further confirmation that the source SC was under outburst. And as I mentioned before, the outburst luminosity of the source was less than 1 solar luminosity of the order of 0.95. And the median luminosity for the non-FUOs from 2018 is approximately 48 times L solar. So when you look at the plot, the source under outburst is located at a very far region. So, and I would also like to point out that the source is still rising, and its outburst luminosity can go as high as it increases. So we are looking onto it, like how long the source will increase in its brightness and how much outburst luminosity it can go up to. So
Yeah, 5
yeah,
minutes.
yeah, yeah. Like that, the source is uh, very interesting opportunity to study this type of outburst in very low luminosity objects, and we are looking forward if it appears in any optical surveys in the future, and how long its outburst goes on. Yeah, to in summary, we have an intriguing outburst from a Velo, transitioning it into an FU Ori-type variable, and it was identified in the mid-IR and confirmed with spectroscopy observations. And we classify this object as an FU Ori-type variable with the potential binary candidate. And I'd also like to highlight that this is one of the lowest luminosity ISOs, which shows this kind of an outburst. And this outburst may represent a pivotal phase in this Velo's life, where it determines whether the object will be a supernova star or a brown dwarf. Yeah, that's all. Thank you so much for listening.
Thank you very much. Thank you very much for this really nice and very interesting object. Do we have questions? There is a question. If you have a microphone.
Hi, Mizna. I'm Koshvin. I might have missed your paper at that time. I just wanted to ask during the outburst, what was the NEOWISE color of the source? Like, did it get blue or redder?
Yeah, the NEOWISE colors was also it was following an interesting pattern. So in the beginning, it got slightly redder, and then it started to get bluer along the like direction of extinction. And then in the recent epochs, it's again tracing back to its previous position. So this was another interesting fact, that the color was going in a cyclic way. So
Okay.
we assumed that it could be an interplay between accretion and extinction.
Extinction from some other material other than the star disk system? Like some other material, like something which is outflowed from the system, and that is extending, that is causing the extinction?
Yeah, it could be. Like when this is going into outburst, there could be, as I showed, there was nebular emission around it. So it could be increasing the extinction. Yeah, we can further look into it in future to see what exactly is going on.
Thanks.
Okay, more question, please.
Hi, Mizna. Really cool result. Are you able to constrain the mass of the progenitor object?
Yeah, but I won't say it was an accurate measurement, because we use this upper limit of 0.2 L solar. It's pre-outburst luminosity and cross-checked with the bonafide models, and it came out to be approximately 0.1 solar masses.
Okay.
That too is not accurate.
Okay, Lee.
So really quickly, it's interesting you have such a low luminosity object. And one thing you might think about is to use the steady disk formulae. You know, the maximum temperature in the disk has to be bigger than something in order for you to see, the infrared, right? It has to be more than 4,000 degrees at least, right? So basically the luminosity goes like the r squared times t to the fourth, right? So if you have some constraint on the temperature, you could try and think about what this implies for the inner radius of the object you're looking at, right? And whether it makes any sense. You see what I mean?
Yeah, we'll look into that.
Yeah, it was also my question whether... I'm sorry, Peter. No. My question would have been, is it really realistic to assume that such a certain not very high accretion rate can make the temperature inversion within the disk? So probably some basic calculations can show that. Do we have any other questions? I would encourage the younger generation to learn about this very interesting source. If everyone knows everything, then let's thank Mizna again. Thank you very much for the talk.